Salutations, mini mathematicians! So happy you could join us. We're going to be doing 5.2 C lesson problem solving with scientific notation. So you've already done a lot of work with scientific notation, multiplying, dividing, rewriting values. So we are going to use that today in some word problems. So the first problem says, use scientific notation and exponent rules to solve each word problem. Write your answer in a complete sentence using standard notation and show all your work. So it says at one time, McDonald's had sold more than 1 billion hamburgers. If it were possible to eat a hamburger every minute of every day, day and night, no stopping, no sleeping, no nothing, how long in years would it take to eat 1 billion hamburgers? Express your answer in appropriate units of time. So we're going to break this problem down. Part A says how many hamburgers were eaten per day? Well, if we know that 1 hamburger is eaten per minute, 1 hamburger per minute, we need to know how many minutes are in a day. So, taking a look here, how many minutes are in a day? Well, we know that we have 24 hours in one day. So if we have 24 hours per one day, and then we multiply that by, there's 60 minutes in an hour, 60 minutes per 1 hour. Notice the hours are going to cancel out with hours. Make that look a little better, I guess. Hours will cancel out with hours, and we'll be left with how many minutes are in a day. So go ahead and grab a calculator. I really like the Desmos scientific calculator, and we're going to do 24 times 60, and we get 1,440. So we know that this is equal to 1,440 minutes per day. So if we know that 1 hamburger is eaten per minute and there's 1,440 minutes per day, how many hamburgers are eaten per day? There are, capital letters, start your sentence, please. There are 1,440 hamburgers eaten each day at this rate of 1 hamburger per minute. Perfect. Remember, you can always pause the video if you need to look at something or if you're having some trouble with the formatting. Totally fine. Awesome. Let's go on to problem number 2. So remember what we saw here. So problem 1b, slide 2. We know that there are 1,440 hamburgers eaten per minute, but now we want to know how many hamburgers are eaten per year. So if we want to know how many hamburgers are eaten per year, we need to figure out how many minutes are in a year. Well, to figure that out, I know that there are 365 days in a year, and we know how many hamburgers are eaten per day. So if we take the number per day and multiply that times 365 days, we will get our answer. So that is our problem solving plan, and it's often really helpful to write down your problem solving plan before you actually start putting in the numbers. So how many hamburgers are eaten per day? That's 1,440, and we're going to multiply that by 365 to get how many hamburgers are eaten in a year. And again, go ahead, pull up that calculator. We already have 1,440 in there, so I just can put times, oh, I guess it didn't save it. So 1,440 times 365, and we press enter. we get 525,600. So 525,600. So how many burgers are eaten per year? Maybe I can do a little Control C, Control V action. There are 525,600 burgers eaten per year at this rate of 1 hamburger per minute. Oof, that is a lot of burgers. Okay, let's take a look at slide 3. So now that we know how many burgers would be eaten in a day and how many in a year, we want to know how many years is it going to take to eat 1 billion hamburgers. Well, if I want to know how many years it's going to take to eat 1 billion hamburgers, I'm going to need to take 1 billion, which is 1 billion burgers. So I'm going to need to take billion burgers and divide that, and divide 1 billion burgers by the number eaten in 1 year. That's going to tell me how many years it'll take to eat 1 billion burgers. Okay, well, we remember that 1 billion, if you want to think about 1 billion, there's 1, and then 1,000, 1,000,000, 1 billion. If we added 3 more, that'll be 1 trillion, which might come in handy later in the lesson. So, and we're going to be dividing that by the number eaten in 1 year, which remember is 525,600. So we know that dealing with these big numbers is not the most efficient way. So what we're going to do is we're going to turn this into scientific notation. So 1, some parentheses, 1 is my significant figure because that is greater than or equal to 1 and less than 10. 1 times 10 raised to the, and how many decimal places would I need to move over? Well, that's 3, 6, 9, and I'm going to the right because it's getting bigger. So 10 to the 9th power divided by this significant figure is going to be 5.256 times 10 to the 5th power. Because if I went to the decimal point and I moved over 1, 2, 3, 4, 5 to the right, I get back to my original number. I'm going to break these up. So I'm going to do 1 divided by 5.256, which would just get you, if you grab your calculator, we could put that in there and I'll let you know you get about 0.19025 and times 10 to the, well, there's 9 factors in the top, 5 factors of 10 in the bottom. 5 will cancel out, 4 will be left over on top, so that's a positive exponent of 4. But remember, we want to put our answer in standard notation. So if I move the decimal over 4 times, 1, 2, 3, 4, that gets you 1,902.5. So about how many years will it take? It will take a person about 1,902 years to eat 1 billion hamburgers if they ate 1 burger per minute. Wow. Always use your spell check. Cool. So you're going to pause the video and finish number 4, and we're going to go over it as soon as you're ready. Okay, let's take a look at problem number 4. So problem number 4 here, it talks about the debt per person. And what we have is the total debt and divided by the total people will be the debt per person. So if we take 15 trillion, the dollar debt, divided by the 300 million working people, we break it into scientific notation and we divide, we get about 50,000. So the national debt per person is about $50,000. Wowzers. And we're going to be using that information to figure out, well, how long would that take one person to pay off? So problem 5, 2B, slide 5, here we have Ashley, and she works at a retail store. She earns $10 per hour, and 18% of her paycheck goes to the federal taxes. So that taxes is going to go to paying off the national debt. So how many hours would she have to work to pay off her share of the national debt? Well, first we have to think about how much per hour goes to the national debt. Well, she makes $10 per hour, and 18% of her paycheck goes to federal taxes. So we need to know what 18% of $10 is. Remember, when we use percents, we have to turn them into decimals. Of means multiplication, so it's 0.18 times 10, which means $1.08 or $1.80. So $1.80 per hour goes towards paying the national debt. So she pays $1.80 towards the debt hour. But then we want to know how many hours she has to work to pay off her share of the national debt. So remember, her share of the national debt is $50,000. So we're going to take 50,000 and divide that by $1.80. When we do that, and you can do that by grabbing your calculator, if we put in 50,000 and divided that by 1.8, $1.80, wow, it's going to be 27,777.7 repeating. Okay, so of course, how many hours will that be? That is going to be, it will take Ashley about 27,777 hours to pay off her share. Her share. I need to learn how to type. Her share of the national debt. Awesome. Okay, well, let's put that in perspective. That seems like so many hours. Well, let's turn that into years then. So I'll let you know that she works 2 times 10 to the third hours a year, and I want to know how many years it'll take her to pay off her portion of the national debt. So taking a look at this, if we take her total hours and divide it by 1 year's worth of hours, we will get our answer. So what are we going to have here? What we're going to have is 27,777. If we write that in scientific notation, so again, we're going to take 27,777 and we're dividing that by the years she works in, hours she works in a year, which they told us was 2 times 10 to the third power. And of course, we're going to rewrite this into scientific notation. So 2.7 times 10 to the, move the decimal over 1, 2, 3, 4, 10 to the fourth power, divided by 2 times 10 to the third power. So from here, we know that 2.7 divided by 2 is about, I guess there'd be a bunch of 7s there. We should not round. Okay. We get about 1.3888 times 10 to the first, which when we rewrite this in standard form, move the decimal over once to the right, that'd be 13.888 years. Okay, so how many years would it take her to pay off her portion of the national debt? It will take Ashley almost 14 years to pay off her share of the national debt. Of course, we all know it's just going to keep on getting bigger, so she's just going to have to keep on working and keep on paying. Nice. Good work here, you guys. Okay, following along, looking at problem 7. So we always want more storage, right? More storage on our phones, more storage on our computers. So here, what we're going to be doing is on a computer, a byte is a unit of information. It's like how much storage you have, right? So a typical document contains tens of thousands of bytes, like one of your English essays or one of your homework assignments you scan in for math. So therefore, it's useful to use the words below to describe storage capacity for a computer, because if there's tens of thousands of bytes and just one upload of a homework assignment, you guys turn in a lot of those. So if we take a look, 1 kilobyte is 1,000 bytes. So I want to know how many, in scientific notation, how many bytes is a kilobyte? So that is 1 times 10 to the third bytes. So 1 kilobyte, and you remember kilo means 1,000, and that's why a kilobyte is 1,000 bytes. Bytes is kind of like that base unit, and then we're moving. So a megabyte is 1,000 kilobytes. So we have all those kilobytes, and then we have it times the bytes. So notice it's going to be groups of 3. It's another 3 decimal places. So 1 megabyte is 1 times 10 to the third kilobytes. So notice it's another group of 3 decimal places because it's kind of like going hundreds, thousands, millions, billions. But here we go, kilobyte, megabyte, gigabyte, terabyte. So notice a gigabyte is 1,000 megabytes. So I'm just going to do a little copy paste action, megabytes. And again, a terabyte is 1,000 gigabytes, so it's 1.1 times 10 to the third gigabytes. So what we're going to do on the next screen is we're going to convert these into how many bytes they are so we can do some math with them. Okay. So here we want to know just in how many bytes. So 1 kilobyte we know is 1,000 bytes from the previous slide. So we're just going to 1 times 10 to the 3 bytes. 1 megabyte, though, you guys, is 1,000 kilobytes. So we have 1 kilobyte is 1,000 bytes, but now we need 1,000 of those. So what's 1,000 times 1,000? That's going to be 1 times 10 to the 6th bytes. So again, what we're doing is we're multiplying each thing by a power of 1,000, and 1,000 is 10 to the third. So when we multiply the previous one by 10 to the third, what do you do when you're multiplying with the same base? You add your exponents. So since a gigabyte is 1,000 megabytes, we're going to take 1 times 10 to the 6 bytes and multiply it by 1,000. So we're multiplying this value up here times 10 to the third. And what do we get here then? We're going to get 1 times 10 to the, you guessed it, 9th bytes. Oops, gotta press the down or the over arrow so we're not stuck in that exponent. And 1 terabyte, you guessed it, that's going to be 1 times 10 to the 9 plus 3, 12th power of bytes. Nice job, mini mathematicians. Okay, so problem 3C, it says if your computer has a memory storage of 16 gigabytes, how much storage capacity, how many bytes of memory this is? So we want to know 16 gigabytes is equal to how many bytes? Well, we know that 1 gigabyte is equal to 1 times, and I'm going to use my little math function down here, 1 times 10 to the ninth, right? 1 gigabyte is 1 times 10 to the ninth bytes. We have to have the same units to use these numbers. That's why we converted all of them into bytes. So that means 16 gigabytes is going to be equal to 16 times 1 times 10 to the ninth. Oops, gotta spell things right. So this is going to be equal to 16 times 10 to the ninth. And if we wanted to write this in scientific notation, that's 1.6 times, and remember, this 16 in scientific notation is really 1.6 times 10 to the first. So 10 to the first times 10 to the ninth gets me 10 to the 10th bytes, which we know is equal to, oh my goodness gracious. So 1, 6, so we move the decimal over once, and I have to go 10 times. So I need 9 zeros. 1, 2, 3, 2, 3, 1, 2, 3. And always go back with your with your commas to communicate clearly, just in case you forgot a 0, right? And of course, we want to write our answer in a nice sentence. So a computer with storage of 16 gigabytes has 16, what is that? Hundreds, thousands, millions, billions, 16 billion bytes of storage. Wonderful. I didn't spell that right either, but didn't catch it. Storage. Nice. Good job. Okay, so what you're going to do is you are going to work on the last 2 slides, answering a few questions about storage and thinking about, are we dividing? Are we multiplying? What are we doing to get to the right answer? So good luck. You're going to do awesome. Pause the video and we will go over them as soon as you're ready. Okay, let's see how we did. Slide 10. So taking a look here, it says how many computers with 16 gigabytes of storage each do we need to buy to get 1 terabyte of memory? So here, if I take 1 terabyte and divide it by 16 gigabytes, because each computer holds 16 gigabytes, so I'm going to take 1 terabyte and split it up, and I'm rewrote them with scientific notation. So I get about 62 and a half computers, and you can't buy half a computer. So you will need 63 computers to have 1 terabyte of memory. Make sure you're showing all your work to get credit. And then on slide 11, it says, if a novel consists about 250 megabytes, how many novels can we store on a 16 gigabyte computer? So if one novel is 250 megabytes and one computer has 16 gigabytes, we're going to take those 16 gigabytes for the computer and divide it by 250 megabytes to see how many novels can fit on the one computer. So when we do that division, we get 64. So about 64 novels can be stored on a 16 gigabyte computer. That's awesome. That's like a year's worth of books, right? Awesome. Great job, mini mathematicians. Excellent work. I hope you're having a wonderful day, and I'll see you next time. Stay psyched, do your best, and be nice to everyone.